Hi everyone, thank you so much for joining today's video. We're going to be learning about Born-Haber cycles, and these are our learning objectives. So we're going to be able to define each of the above terms and lattice enthalpy. So that's enthalpy of formation, ionization energy, enthalpy of atomization, bond enthalpy, and electron affinity. And then we're going to construct Born-Haber cycles to calculate lattice enthalpies using these enthalpy changes. And then we're going to construct Born-Haber cycles to calculate one of the other enthalpy changes. And then we're going to compare lattice enthalpies from Born-Haber cycles with those from calculations based on a perfect ionic model to provide evidence for covalent character in ionic compounds. And then we're going to be able to define the term enthalpy of hydration and perform calculations of an enthalpy change using these cycles. So the enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements with all reactants and products in their standard states under standard conditions. And it's really important that you remember some key things about the enthalpy change of formation because it needs to be exactly right to be the standard. So things to remember are that 1 mole of a substance is formed from its constituent elements with all reactants and products in their standard states and under standard conditions. So for example, we could have water, and that's made out of the constituent elements of hydrogen and oxygen. And then we would have to sort out balancing the equation for the equation of the enthalpy change of formation. And we denote the enthalpy change of formation as delta HF. And that symbol means standard. Ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And the things to remember about ionization energy are that you're removing 1 mole of electrons from 1 mole of gaseous atoms. And so everything needs to be in their gas states. For example, the first ionization energy is the energy required to remove 1 mole of the outermost electron from 1 mole of gaseous atoms, and this forms +1 gaseous ions. The enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms is produced from an element in its standard state. So the important things to remember are that 1 mole of gaseous atoms are produced, and they're produced from an element in its standard state. And so, for example, we could have iodine. So we want to produce 1 mole of gaseous iodine. So that's what we have as the product. And so we need half an iodine molecule. And iodine normally comes as a solid in its standard state. And we denote the enthalpy of atomization as delta H at with the small symbol for standard. Bond enthalpy is the enthalpy change when 1 mole of covalent bonds is broken in the gaseous state. So another name for bond enthalpy is bond dissociation enthalpy. And the important things to remember are that 1 mole of covalent bonds is broken in the gas state. And so, for example, we could have iodine. So we have iodine, and that's going to be in the gas state. And then we're going to form 2 iodine atoms, which are also in the gas state. And this is because we're breaking this II bond. And the way we denote bond enthalpy is by delta H standing for dissociation and the symbol for standard. So electron affinity is the opposite to ionization energy. It's the enthalpy change when each atom in 1 mole of gaseous atoms gain electrons to form 1 mole of gaseous negative ions. And so the important things to remember are that each atom in 1 mole of gaseous atoms gain electrons to form 1 mole of gaseous negative ions. And so, for example, the first electron affinity would be the enthalpy change when each atom in 1 mole of gaseous atoms gain 1 electron to form 1 mole of gaseous 1- ions. And so, for example, we could have oxygen, 1 mole of oxygen, and we're going to add an electron to it to form O- ion. And this would be the first electron affinity. And the way we denote electron affinity is by delta H with a small EA and then the standard symbol. The lattice enthalpy of formation is the enthalpy change when 1 mole of a solid ionic compound is formed from its constituent ions in the gas phase. So the important things to remember are that it's 1 mole of a solid ionic compound which is formed from its constituent ions in the gas phase. So for example, if we were going to form magnesium chloride, we would have magnesium ions in the gas phase and chloride ions in the gas phase, and that would form magnesium chloride, the solid ionic compound, and then we would balance it by using 2 chloride ions. And the way we denote lattice enthalpy of formation is by delta H, LEF, and then the standard symbol. The lattice enthalpy of dissociation is the enthalpy change when 1 mole of a solid ionic compound is broken up into its constituent ions in the gas phase. So the important thing to remember is that it's 1 mole of a solid ionic compound which is broken up into its constituent ions in the gas phase. And so, for example, if we had sodium chloride, we started off with 1 mole of solid sodium chloride, we would then split that up into the sodium ion, which is a gas, because we're doing it in the gas phase, and also a chloride ion, which is in the gas phase. And how we denote lattice enthalpy of dissociation is by delta H, LED, and the standard symbol. The enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions become hydrated, so that means dissolved in water, and this forms aqueous ions. So the important things to remember are that we're measuring the enthalpy change when 1 mole of gaseous ions become hydrated, so you add water to them to form aqueous ions. So for example, we could have magnesium ions, and these need to be gaseous, and then we write plus AQ, which just means that we're dissolving them in water, and so this will form Mg2 plus aqueous ions. So we're using 1 mole of Mg2 plus gas ions to form Mg2 plus aqueous ions. And the way we denote enthalpy of hydration is by delta H, HYD, and then the standard symbol. So now we're going to talk about calculating the enthalpy of solution. Now the definition of the enthalpy of solution is the enthalpy change when 1 mole of an ionic solid dissolves in an amount of water large enough so that the dissolved ions are well separated and do not interact with each other. And the thing is, we can use a cycle to calculate this enthalpy of solution given the enthalpy of hydration and lattice enthalpy of formation. So the definition of enthalpy of hydration is when we hydrate, so when we add water to 1 mole of gaseous atoms and turn them into aqueous atoms. So the definition of enthalpy of hydration is when we hydrate, so when we add water to 1 mole of gaseous ions and turn them into aqueous ions. And the definition of the lattice enthalpy of formation is when we form 1 mole of a solid ionic compound from its constituent ions in their gas states. And so we can see that we can have a cycle kind of like this. So you'd have gas ions at the top, and then you'd have the ionic solid, and then you'd have dissolved ions. So to go from the gas ions to the dissolved ions, these would be the hydration values. So these are the hydration enthalpies, because that's the definition of hydration enthalpy, is basically adding water to these gas ions to turn them into dissolved ions. And then from gas ions into ionic solid, this is the lattice enthalpy of formation. Because we're using the constituent ions in their gas state to form the ionic solid compound. And so then we can work out this ionic solid to dissolved ions. And this is what the enthalpy of solution is. So we're changing 1 mole of an ionic solid into its separated dissolved ions. And so this is the delta H of solution. This is how we write it. And so this is this kind of cycle that we get. So for this example, calculate the enthalpy of solution of magnesium chloride, given that the lattice enthalpy of formation of magnesium chloride is minus 2,493 kilojoules per mole, and the enthalpies of hydration of magnesium and chloride ions are minus 1,920 and minus 364 kilojoules per mole respectively. The first thing we do is we'll start off with the gas ions at the top. So what I can do is, your cycle can look like the one I've just drawn, or it can be slightly rearranged. So I quite like to have the gas ions at the top and the ionic solid at the top. So I would write it like this. So you would have Mg2 plus ions, and these would be gaseous. And then I'm going to add them with chloride ions, which are also gaseous, to form this ionic solid, the magnesium chloride, which is a solid. And then I balance it using 2 chloride ions, and this will be my lattice enthalpy of formation. So this will be my minus 2493. And then what I have is I then write the dissolved ions. So I would have Mg2 plus aqueous and 2Cl minus aqueous. And then to get from Mg2 plus gaseous and Cl minus gaseous to the aqueous versions, we would use the hydration enthalpies. And so the hydration enthalpy for the Mg2 plus is minus 1920. And the hydration enthalpy for chloride ions are minus 264, but we've got 2 of them, so we have to do 2 times minus 364. And so that totals up to minus 2,648 kilojoules per mole. And so now we can find this when we dissolve this solid ionic compound into its aqueous ions. And this is what we're trying to find. This is the delta H of solution. And so now we can use Hess's law idea. So if we start here and we end here, then the 2 roots should have the same enthalpy. And so we form an equation. So our equation is minus 2,648 equals minus 2,493 plus delta H of solution, and rearranging that gives that the delta H of solution is equal to minus 155 kilojoules per mole. Now we're going to learn about Born-Haber cycles. So the lattice enthalpy of a compound can be found using a Born-Haber cycle, and this value is often called the experimental value, as all the data used in these cycles are determined by experiments. So if you can remember, the lattice enthalpy of a compound is the enthalpy change when 1 mole of that solid ionic compound is either formed or dissociated into its gaseous constituent ions. And a Born-Haber cycle is one which includes all the enthalpy changes in the formation of an ionic compound. In these cycles, the lattice enthalpy is usually shown as the lattice enthalpy of formation, and this is so that we can write an equation where the enthalpy of formation of the ionic compound will equal the sum of all the other energy changes. And so there are a few rules to drawing these cycles. So the first is to draw a separate step for every enthalpy change. And so we can see on there, on this example of a general Born-Haber cycle, that the lines represent the steps. So we have, for example, this atomization of metal and non-metal. So that would be one step. And then we would have another step where you get the ionization energies of metal atoms. The second rule is that second and third electron affinities are endothermic. And so they have to have arrows going up, as we'll see later. So the electron affinities one is actually something to remember, because the first electron affinity is exothermic, but the ones after are all endothermic. And that's because for the first electron affinity, you're adding an electron, which is fine. But then for like the second electron affinity or the third electron affinity, you're adding electrons onto an already negative ion. And so that requires a lot of energy, so it becomes endothermic. The third rule is to write the numerical values of the enthalpy changes on each step. So on this example one, for example, we would have like plus 273, for example, and this could be minus 847. Of course, I've just made those numbers up, but normally the questions will ask you to calculate one of the enthalpy changes. So if you've got all the numbers written down, then it'll be easier for you to see how to add it all up. And the fourth rule is that an arrow down indicates an exothermic reaction and an arrow up indicates an endothermic reaction. So as you can see how I've labelled the numbers, so this arrow up would be a positive because it's endothermic, so this is the enthalpy change. So that would be positive. And this one over here, the arrow is going down, and so the enthalpy change will be negative, like we've learned already. And now you can see that the enthalpy of formation is equal to the sum of all the other enthalpy values. And this is building on Hess's law. So Hess's law states that no matter what route you take, the enthalpy change will be independent. So this means that if we follow the arrows round, then this enthalpy of formation, this will be equal to the sum of all the other enthalpy values. And that's because we're starting and finishing in the same places. So we're starting on this level, and then we're finishing at this solid ionic compound level. So we're going to look at an example. Find the enthalpy of formation of magnesium bromide by drawing a Born-Haber cycle and using these enthalpy changes. So the first thing I like to do is to write out all the equations for the enthalpy changes, so I know exactly what's going on. So first we've got the first ionization enthalpy of magnesium. First ionization enthalpy is the enthalpy change when 1 mole of electrons, or the outermost electron from 1 mole of gaseous atoms are removed. So that forms 1 mole of gaseous 1+ ions. And so the equation would look like this for magnesium. So you'd have magnesium in a gas form, and then 1 electron would be taken away from it. So it would form an Mg plus ion, which would be gaseous as well, and then plus an electron. So if I label these 1, 2, 3, 4, 5, and 6, and then now we can write out the equations. So that's our first equation. And then our second equation, the second ionization enthalpy of magnesium, that would be removing 1 mole, removing the outermost electron of 1 mole of Mg plus ions in the gas phase to form 1 mole of Mg2 plus gas ions. And so we have Mg plus, which is the gas, and another electron is removed, so we get an Mg2 plus ion, which is a gas, and an electron. And so for number 3, the first electron affinity of bromine, that's the opposite of ionization energy. So it's the enthalpy change when we add an electron to 1 mole of bromine atoms to form bromide ions. And so for number 3, we get 1 mole of bromine which are gases, and then we add one electron to them, and they form bromide ions, which are also gases. For number 4, the atomization enthalpy of magnesium. The definition of the atomization enthalpy is the enthalpy change when 1 mole of gaseous magnesium is formed from magnesium the solid. And so the equation we have is that magnesium solid will be atomized to form 1 mole of magnesium, which is gas. And then it's a similar thing for number 5. So we have bromine, and that's normally a liquid, and this will go to form bromine, which is a gas, and 1 mole of it. And then for number 6, the lattice enthalpy of formation of magnesium bromide. The definition of lattice enthalpy of formation is the enthalpy change when 1 mole of that solid ionic compound is formed from its constituent ions in the gas phase. And so magnesium bromide is made out of magnesium 2 plus ions and bromide ions. So that's what we have. We have magnesium 2 plus ions, which are gaseous, and then we have bromide ions, which are also gaseous. And they go to form this magnesium bromide compound. So it's a solid. And that means that we need 2 of these bromide ions. And so these are all our equations. So now we're going to construct the Born-Haber cycle. One thing to keep in mind is that you'll need quite a big space for this. So don't start off doing it really small. And so I'm just going to zoom out, and I'm going to write the numbers back on so I know what everything is. So I'm going to write all these numbers here so we can see them. So I've got 736, 1450, minus 342, plus 150, plus 112, and minus 2394. Okay, so now it's all a bit more clear. So we don't hear the question anymore. So what I like to do is I start off with what we're trying to find. So we're trying to find the enthalpy of formation of magnesium bromide. And what that means is we're forming 1 mole of magnesium bromide from its constituent elements in their standard states. And so we have, I'm just writing out the equation so I know what it is. So we've got magnesium, which is a solid in its standard state. I'm going to add it with bromine, which is a liquid in its standard state. And this is going to form magnesium bromide, the solid. It's a solid ionic compound. And so that should be MgBr2. And so now we can get on to the actual cycle. So I start off with this side of the equation and I plot it down. So I'm just going to zoom out a bit further. So I'm going to plot it quite far down. So magnesium plus bromine liquid. And instead of putting the right side of the equation on the right like we normally do, I'm going to put it underneath. So I have a magnesium bromide solid underneath. And then I use a ruler and I draw some lines. So this line represents a level. And then I'm going to draw for this is the bottom section of it. I'm going to draw a longer line, because what we'll end up with is a cycle where we'll have this start and we'll have an arrow going down, but then these arrows will all go towards this direction. So they'll all go towards this bottom product. So we'll start here. This is where the magnesium and bromine is, and we'll finish here. And so that's why I'm making the bottom line quite long. And so to get from this magnesium solid and bromine liquid to the magnesium bromide, it's an exothermic reaction. We know that because when we form bonds, energy is released. So that arrow goes down, And that's the value we're trying to find. So I'm going to call that delta H of formation. And then I draw the next level. And it's up to you what reaction you choose to do next. But I quite like to atomize things first. So I'm going to use equation number 4 to atomize magnesium to magnesium gas. So one level above, I'm going to write magnesium gas. And then I'm going to just leave the bromine alone. So it remains the same as it was in the previous level. And then we draw another straight line again to represent the level. And then I'm going to draw an arrow up. And this indicates that it's an endothermic reaction. We know this because this value here is positive. And we also know that energy needs to be supplied to a solid in order to break apart all the atoms so that there's no forces between them like there is in a gas. And so the reaction is endothermic because it's taking heat energy in. And then now I like to write in the number. So we have plus 150 here. And then the next thing I'll do is atomize the bromine. So like we did for magnesium. So I'm going to leave the magnesium gas alone. And then I'm going to atomize the bromine. And then draw the level line again. So a really important thing to remember here are your definitions for all of the enthalpy changes, because equation 5 that we've written is the atomization enthalpy of bromine. But you need to remember that the definition of atomization enthalpy of bromine is that we're producing one gaseous mole. So because here we're forming 2 gaseous moles of bromine, that means that we need to times the plus 112 kilojoules per mole by 2, because we're using 2 times the atomization enthalpy of bromine. And so we draw an arrow up because it's endothermic again. And then this time the number is going to be 2 times 112, which equals plus 224. And then what I'll do is well, first of all, I'll tick off the ones that we've already done. So we've done number 4 and we've done number 5. So the next thing I can do is use the ionization energies. So I can use the ionization energies of magnesium, so the first one and the second one. And so I can write in the first ionization energy of magnesium. So I get a magnesium gas, but it's going to be a plus ion now. And then I'm going to also still get the 2Br gas. I'm not changing anything about that. But I get an electron because I've taken an electron from the magnesium gas to form an Mg plus gaseous ion. And that's our next level. And then I draw another arrow up because that's also endothermic. And that comes out to be plus 736. As well as writing the numbers, because you're also doing calculations sometimes, like I've done with 2 times 112, it's nice to just highlight them as well so you know which numbers you're actually wanting to read off. So that makes it slightly easier to see. And then the next thing I'll do is the second ionization energy of magnesium. So that will be Mg, and now it's become a 2 plus ion because we're going to take another electron off, and then the bromine doesn't change, and then we're going to have 2 electrons, and then draw another line. And this is actually going to be our top level because that's the end of our endothermic reactions. And this value is plus 1450. So now we have 2 equations left. We have the first affinity of bromine and also the lattice enthalpy of formation of magnesium bromide. And so what we put next is this electron affinity of bromine. And so what we get when we take the electron affinity is we add one electron to one bromine. And so what we get is the Mg2 plus ion, which hasn't changed. And then we get 2 Br minus gaseous ions. And what we've done here is actually we've used 2 times the electron affinity of bromine, because we have formed 2 bromide ions instead of 1, like in equation 3, because we had 2 electrons spare, so we've just added 2 electrons to it. Well, we've added 1 electron to each bromine to form 2 bromide ions. And so now we draw an arrow going down, because the first electron affinity is exothermic. So this number is minus 342. And then finally we have this lattice enthalpy of formation of magnesium bromide. And now you can see that actually this is just this reaction here, because we're going from the gaseous constituent ions of magnesium bromide to form the solid ionic compound. And so this value is minus 2,394. And I'm just going to highlight that so we know which numbers to look at. So we can now calculate the enthalpy of formation of magnesium bromide by using kind of Hess's law idea. So I can see that this arrow here, so if we call this the start and this the finish, we can see that this enthalpy change should be the same as if we go all the way round clockwise to the finish. So if we followed all these arrows through right to the end, those 2 enthalpies should be the same. And so we can form an equation. So what we get is delta H of formation is equal to 150 plus 224 plus 736 plus 1,450. That's supposed to be minus 2 because we used 2 electron affinities of bromine, sorry. So that will be minus 342 times 2. Minus 342 times 2, which is equal to minus 684. So that's the number that we need. And so we add that on. So that would be minus 684 minus 2,394. And this gives us a value of minus 158 kilojoules per mole. So by using this cycle, we found the enthalpy change of formation of this magnesium bromide by using all of these other enthalpy changes. And that's the whole point of these cycles, is to find something from using a longer process of all the enthalpy changes in order to get to the same thing. So we can actually calculate any of these enthalpy changes. It doesn't have to be this enthalpy of formation. We can calculate any of them given all of the other ones, just by forming an equation like this one. And also, it's useful sometimes to annotate what you've done. So, for example, for this bit, you could say this is the first ionization energy of magnesium. And if you do that, then you're less likely to confuse yourself. But obviously, after a while, you could stop doing that if you wanted to. Sometimes exam questions might ask you to write them as well. So it's important that you've got the equations on the different levels and that you write the steps that you're doing. Now I'm going to introduce this idea of a perfect ionic model. And what this model assumes is that, first of all, ions are perfectly spherical, and second of all, the ions display no covalent character. So what it's saying is that if I have two ions, such as X plus and X minus, then the distribution of electrons is perfectly spherical around the ions, like this. And I'm going to use this model in when we compare experimental to theoretical lattice enthalpy values. And I'm going to talk more about this perfect ionic model when we come to comparing the theoretical and experimental values for the lattice enthalpies. So now I'm going to talk about comparing experimental and theoretical lattice enthalpies. So first we're going to look at the trends in lattice enthalpy. So number one is that larger ions have a smaller lattice enthalpy of formation, as the opposite charges do not attract each other as closely compared to if you had smaller ions, because the charges in the middle, there'd be less space between them if we had small ions, and so they would have a higher lattice enthalpy compared to larger ions. And then secondly, when you have ions with stronger charges, they have a higher lattice enthalpy of formation, as they give out more energy when they come together into the solid. So for example, if you had an ion with double the charge, then it would give out double as much energy when it forms into the ionic solid. So the value of the experimental lattice enthalpy, and we call this the true value because this is the value that we've calculated using experiment, is better than the theoretical value of the lattice enthalpy. And the theoretical value of the lattice enthalpy actually assumes the perfect ionic model. So it plugs that so the theoretical value of the lattice enthalpy is calculated using an equation, but it assumes the perfect ionic model. And so the reason why it's not very accurate is because there is often distortion. So that's another word for polarization of ions in an ionic compound. So the ions are not perfectly spherical like they are assumed to be in the perfect ionic model. And we say that they have covalent character. So two facts are that positive ions that are small and or highly charged are very good at distorting, so polarizing negative ions, and that's because they have a greater charge density. And negative ions that are large and or highly charged are easier to distort, so they're easier to be polarized. And in general, a bigger difference in the lattice enthalpy means the greatest covalent character. So if there's a really, really big difference between the experimental and the theoretical lattice enthalpy, then that means that there's quite a lot of covalent character. And so the magnitude of the lattice enthalpy indicates the strength of the ionic bonding, so how big the number is. But the difference between these two experimental and theoretical values indicates the amount of covalent character this ionic compound has. So if we have a look at this table at the bottom, we can see that for sodium chloride, the difference is only 0.6%. So that indicates that the bonding is almost purely ionic with very little covalent character. So the sodium and chloride ions must be quite. However, if we look at the lithium chloride, for example, the difference is 1.5%. So it indicates that the bonding is still very ionic, but there's a little more covalent character than the sodium chloride. And that's because the lithium plus ion is smaller than the sodium plus ion. And that's because lithium is up a group compared to sodium. So that means that the lithium plus is better at polarizing the negative ions. And so what happens is that you have the lithium plus ion and you have the chloride ion, but because the lithium plus is better at polarizing, that means that electrons will be more gathered towards the lithium plus ion, and so there will be some distortion. So the ions are not perfectly spherical anymore, because all the electrons will be attracted more to the lithium plus. If we have a look at silver chloride, the difference is 14.9%, so that indicates it's got quite a lot of covalent character. So compounds with the most covalent character would be covalent structures. So they have the most covalent character. And then after that, it would be ionic structures, and then eventually metallic. So this is increasing covalent character. So now we're going to move on to some questions. So for number 1, calculate the lattice enthalpy of formation of aluminium oxide, given that the enthalpy of formation of aluminium oxide is minus 1,669 kilojoules per mole. So for my example, I started with writing out all the equations from the definitions of the enthalpy changes. And after you get some practice and you have a bit more of a go at these kinds of questions, you probably won't need to do that anymore. So I'm just going to start constructing the cycle straight away. So I'm going to start with the enthalpy of formation like we always do. And these will be our bottom 2 layers. So we have, we're trying to form aluminium oxide from its constituent elements, so aluminium and oxygen. So I have aluminium, which is a solid in its standard state, and I'm going to add some oxygen, which is a gas in its standard state, and that's going to form Al2O3, the solid. I know that formula because of the ions that they form. So Al forms +3, 3 plus ions, and oxygen forms 2 minus ions. So that means the ratio is 2 to 3. So for every 2 aluminium ions, I need 3 oxygen oxide ions to balance the charge out. And so that's why the formula of aluminium oxide is Al2O3. And so now we need to balance this equation. So that means I need 2 aluminiums and 3/2 oxygens. And then I draw the lines to indicate the levels. And we draw the bottom one a bit longer. And now I have an arrow going down because this is an exothermic reaction, because we're forming bonds, so heat energy is given out. And I put in the value of minus 1,669. And I'm just going to highlight that so it's easier for me to see when I'm looking at the figures later. And then the next thing I'll do is we're going to do all the endothermic reactions. So the atomization ones and the ionization enthalpy ones. So I'm going to start with the atomization of aluminium. When you get a bit more used to doing these kinds of questions, you can probably do like more than one step at one time, but I'm just going to write them all out so it's really clear. So the enthalpy of atomization of aluminium is when we form 1 mole of gaseous aluminium from aluminium the solid, so like aluminium in its standard state. And so we're going to form aluminium, and these are all going to be gases now. And then I'm going to leave the oxygen alone. So an important thing to remember is the definitions. So the definition of the enthalpy of atomization of aluminium is when you form 1 mole of aluminium gas. And because we form 2 moles, that means we need to times this 314 kilojoules per mole by 2. And so first we draw an arrow going up for this exothermic reaction. And then we have to do 2 times 314. And that gives me plus 628 kilojoules per mole. And this is the number that I highlight. And then the next thing I do is we'll do the enthalpy of atomization of the oxygen. And so I leave the aluminium alone and I atomize the oxygens. And now we remember the definition again. So the enthalpy of atomization of oxygen is when we form 1 mole of oxygen, but we've actually formed 3 here. So we need to times this figure for the enthalpy by 3. So we draw an arrow representing the exothermic reaction, and then we have 2 times 248, 496 joules. And then we highlight this. So as you can see, it's really important to leave yourself quite a lot of room because it can get really crowded. So to make it easier for yourself to read all the numbers later, make sure to maybe put the numbers in different colours or highlight them, and also use a lot of space on the paper. Then the third thing I'll do is I'll start on the ionization enthalpies. So first of all, we have the first ionization enthalpy of aluminium. So we're forming 1 mole of Al plus gaseous ions from 1 mole of Al gaseous atoms. And so what we form is Al plus, and we're just going to have the oxygen still there. And that means that we have 2 electrons because we've removed an electron each from each aluminium atom. And because the first ionization enthalpy is only measured for 1 aluminium and we've done it for 2 aluminiums, that means we need to times the number by 2. So we draw the up arrow, and then we need 2 times 577. And that equals 1,154. And then now I'm going to continue with the second ionization energy. So that's when we form 1 mole of gaseous 2 plus ions. So we'll have 2Al2 plus 3 oxygens, which are left unchanged again. And then now we're going to have 4 electrons because we've removed another electron each from each of the aluminium plus ions. So as you can see, it's really important to remember all the definitions and all of the key words from the definitions because it's really easy to get the numbers wrong. So we draw an arrow, and then we've done it with 2 Al plus ions, so that means we need 2 times the 1,820. And that comes out to be plus 3,640. And then again, we do the same thing with the third ionization energy. So we're forming 1 mole of Al3 plus ions from 1 mole of Al2 plus ions. And then we leave the oxygen unchanged. But now we have 6 electrons because again we've removed 1 electron from each of the Al2 plus gaseous ions. Then an arrow up, and now we're going to have 2 times 2,740, and that equals 5,480 kilojoules per mole. And now this should be our top layer because that's the end of our endothermic reactions. So what you need to remember is that you start off with the enthalpy of formation, which we have at the bottom, and we place those at the bottom. And then you have the solid ionic compound right at the bottom. And then going up from the aluminium solid and oxygen gas, you have atomization and ionization energies. And then we'll move on to do the electron affinities, and then finally it'll be the lattice enthalpy of formation on the other side. Now another thing which will be very useful to do, is to actually label all the different steps that you've done. So for example, this one would be the delta H of formation. This one would be the delta H of atomization of aluminium. And then this is the delta H of atomization of oxygen. And then this one would be and then this one would be the delta H of ionization energy. And this one would be the delta H of ionization energy of this aluminium. And then we have the delta H ionization energy, we can put second, of the aluminium. And then this would be the third. And it's up to you whether you label these or not, but it is very nice to, and it will be helpful for you to see if you have gone wrong, or if you have used every single thing that they've given you. So now we use the electron affinities. So the first electron affinity is negative, so we know that's exothermic, and that means that this has to go down. So for this line, I'm just going to draw it a bit longer. And then in the next level, we have, we'll now leave the aluminium ions alone. And we're going to have the first electron affinity of oxygen. So we're forming 1 mole of O minus gaseous ions. So we're going to form O minus ions, and that's going to use up 3 of the electrons, because we're going to give 1 electron to each of the oxygen atoms, and we've got 3 oxygen atoms, and that means we've used up 3 electrons. Then we draw the line again. Again, we need to remember the definition. So the definition of electron affinity is when we form 1 mole of O minus gaseous ions. And because we've formed 3 of them, we need to times the enthalpy by 3. And so first we draw an arrow going down because it's now an exothermic reaction. And then we have 3 times minus 1004 and that is equal to minus 426. And then we look at the second electron affinity of oxygen. And it's really important to note that this is actually endothermic. And the reason being is because the first electron affinity is when we add an electron to an atom. But the second electron affinity is when we add an electron to an already negative ion, a -1 ion. And so it requires lots of energy. So energy is taken in, and therefore it's an endothermic reaction. So actually, the electron affinities, the first one is always exothermic, but after that, they're all endothermic because you're adding more electrons. We're trying to add more electrons onto an already negative ion. And so then we have a layer going up. So we'll have the aluminiums which stay as they are. Just going to zoom out. So we have the aluminiums which stay as they are, and then we'll have 3 O2 minus, which are gases, and that's used up all the other electrons. So we have no other electrons left because we've given 1 electron to each of the O minus gaseous ions. And so then we draw the line, and now we draw the arrow up, and we label it. It will be 3 times the plus 844, which equals, so at this point you can see that it gets really cramped. We get plus 2,532. And of course you can label these two as well. So we've got this delta H of the electron affinity of this oxygen, and then here we have the delta H of second electron affinity of oxygen. And then what we have is, now you can see that we've ended up with the lattice enthalpy of formation equation, because we've got this two Al3 plus gaseous ions and three O2 minus gaseous ions, and they come together to form this solid ionic compound, this aluminium oxide. And so if we draw an arrow straight down and we extend this bottom line further, this will give us our value for this lattice enthalpy of formation. And so now we can work out what it is by applying Hess's law and following all the arrows through. And so what we do is we form an equation. So this arrow here should be equal to the sum of all the values, all the other arrows going down back to this solid line. And that's because we're starting at this point and we're finishing at this solid line. And so by Hess's law, the enthalpies should be the same, because we're just taking different routes to get from the same start to the same finish. And so we can form this equation. We have minus 1,669, and that's equal to 628 plus 496 plus 1,154 plus 3,640 plus 5,480 minus 426 plus 2,532 plus this delta H of lattice enthalpy of formation. And so rearranging that, you can then find this delta H of lattice enthalpy formation. So we get the enthalpy change for the lattice formation is equal to minus 15,421 kilojoules per mole. Now, the lattice enthalpy of formation, or any enthalpy of formation, will always be negative. So if you've got a positive figure, then you might have done something wrong along the way, and you should check everything. Actually, checking it again, this stage that we've done here, where we've converted the 3.5 oxygens to 3 oxygen gaseous atoms, this value is supposed to be 3 times 248, and so it's not 496. That's equal to plus 744. And so here we have plus 744. And now this should give us the minus 15,421. So you see how important it is to check, because it's very easy to make these silly mistakes. And it's also very important to remember that that second electron affinity is exothermic, so we need to have the arrow going up, and the levels don't keep going down like they normally do for simpler questions. So before I start on question 2, feel free to click off the video and try it yourself first. So we're going to be calculating the enthalpy of hydration of bromide ions, given that the hydration enthalpy of barium ions is minus 1,360. The lattice enthalpy of formation for barium bromide is minus 1,937, and the enthalpy of solution of barium bromide is minus 38. So I first start off with the ions, but in their gas state. So what we know about this is this should be the cycle that we form with the lattice enthalpy of formation, the hydration enthalpies, and the enthalpy of solution. And so in our cycle, we should have the gas ions, the ionic solid, and the aqueous ions. And so I'm going to choose to start off with the gas ions. So we have barium 2 plus gas ions, and also bromide ions. And this should form barium bromide. And this is the solid ionic compound. This will give us the delta H of lattice enthalpy of formation. And now we need to balance the equation, so we need 2 bromide ions. And then we'll put in the ions, but in their aqueous states. So we have Ba2 plus aqueous plus 2Br minus aqueous. And going from the gaseous ions to the aqueous ions, these are the delta H of hydrations, because we're adding water to these gas ions to form aqueous ions. And then to get from the barium bromide to these aqueous ions, we're basically getting the delta H of solution of this solid ionic compound, because we're adding enough water to it to separate the ions enough so that they all become separate. And so now we can put in the numbers. So we have minus 1,937 at the top, and then we've also got the enthalpy of solution, which is minus 38. And then for hydration, we've been given the barium ions, so that's minus 1,360, and we don't know the bromide ions. However, we need to remember the definition of enthalpy of hydration of bromide ions, and that's 1 mole of bromide aqueous ions formed by bromide gas ions. And so because we're forming 2 moles, that means we need 2 times this unknown value. So I'm going to call the unknown value x, and we're just going to add 2x onto the minus 1,360. So this is 2x minus 1,360. And now we can use Hess's law to work out this x. If we start from here and finish here, both routes from start to finish should give us the same enthalpies. And so now we can form the equation. We have minus 1,937 minus 38, and that equals 2x minus 1,360. And this gives us 2x equals minus 615 after rearranging, and then this gives us x equals minus 307.5 kilojoules per mole. Hi everyone, thank you so much for clicking onto the video. Now we're going to look at some harder questions. So for the first question, write an equation for the process that has an enthalpy change equal to the electron affinity of chlorine. And so the definition of electron affinity is the enthalpy change when you add an electron to 1 mole of gaseous chlorine atoms to form 1 mole of gaseous 1 minus chlorine ions. And so what we're doing is we start off with 1 mole of chlorine gas, and then we add 1 electron, and we form 1 mole of Cl minus gas ions. And then for B, in terms of electrostatic forces, suggest why the electron affinity of fluorine has a negative value. Well, because we're adding an electron, there's a force felt between the positive nucleus and the electron. And so energy is released because there's a kind of bond, an electrostatic force forming between them. And so energy is released. So it's an exothermic reaction. So the enthalpy change will be negative. So there's a force between positive nucleus and negative electron, and this means that energy is released. And then for C, complete the Born-Haber cycle for silver fluoride by adding the missing species on the dotted lines and calculating the bond enthalpy of the fluorine-fluorine bond. Okay, so at the bottom we always start with the enthalpy of formation. So we're trying to form the silver fluoride, and so the other thing we need is fluorine. And fluorine exists as a diatomic molecule, so in 2s, and it's also a gas. And so to balance it, that means we need half of these fluorines. And then the next thing that happens is that you see that this silver has now turned into gas. So because we represent one change using one level, that means that the fluorine hasn't changed. So we've still got half of that fluorine gas. And then the next thing that happens is that they've taken the first ionization energy of silver. So again, the fluorine is unchanged. And then to get to the top, they haven't done anything. So that means that we need to change this fluorine. And if you have a look at the other side of the cycle, they have F minus, the gas. And so this gives us a clue as to what we need for this top level. And we actually just need fluorine as an atom, as a gaseous atom by itself. Actually, for the level that we've just done, we need an electron because they've taken an electron away from the silver to get the first ionization energy. And then for the top level, we're going to form 1 mole of fluorine, and we're still going to have that electron because we haven't done anything with it yet. And then this should work because the next thing that happens is that they take the electron affinity for fluorine, which means they've added that electron to the fluorine to form F minus gas. So all of this works. And now it tells us to calculate the bond enthalpy. So I'm going to write all the numbers in a different color. So the first one we have is this enthalpy of formation for the silver fluoride. So that's minus 203. And then the next thing that happens is that we atomize the silver. And so we have plus 298. And then the next step is they've taken the first ionization energy for silver. So that's going to be plus 732. And then for this step, we have to be really careful because we need to remember our definitions. They have broken that bond. So we're trying to find this bond enthalpy, which means that we're breaking 1 mole of these FF covalent bonds. And because we're only breaking half of them, that means we need half of this value. And so what we have is, because it's unknown, and what we have is that because it's unknown, we call it X, but we actually have half of X because we're only breaking half a mole of these FF covalent bonds. And then the next thing that happens is this electron affinity for fluorine, and that is minus 348. And then the last thing that happens is that we've got the enthalpy of lattice dissociation for silver fluoride. So that means we're breaking the solid ionic compound into its separate constituent ions in the gas phase. And so that's why the arrow is going up. And this is plus 955 because it's an endothermic reaction. And so now we can start to form the equation for trying to get the unknown bond enthalpy. And so we use Hess's law and we think, where should I start and where should I finish? So there are a few ways that you can do this. Some people like to swap the signs around so that they can do the same thing as we've done before, but just swap the 203 and the 955 into plus 203 and minus 955. So that works. Or you can choose to start and finish somewhere else. So if I choose to start here, but I finish here, then I can keep all the signs as they are, but it will still work. So we have an equation that looks like this. We have 298 plus 732 plus half x minus 348, and that is equal to minus 203 plus 955. And rearranging that gives us that half x equals 79. And so this gives us that x is equal to plus 158 kilojoules per mole. And it should be a positive number because we're breaking covalent bonds, so energy is needed for that. So it's endothermic reaction. Before I go on to question 2, feel free to try it out for yourself first. So a theoretical value for the enthalpy of lattice dissociation can be calculated using a perfect ionic model. And the theoretical enthalpy of lattice dissociation for silver fluoride is plus 870 kilojoules per mole. Explain why this theoretical value is different from the experimental value that can be calculated using a Born-Haber cycle. Well, the key thing to remember here is that when they calculate this theoretical value, they assume that perfect ionic model. And this means that they assume that the ions are perfectly spherical. And this isn't the case because ionic compounds actually have some covalent character depending on the compound. And so the answer is that there is some covalent character present. And therefore we cannot assume the perfect ionic model as it will be inaccurate because that's assuming that all the ions are perfectly spherical, whereas if they have some covalent character, then we've got some polarization, so some distortion of the ions. And then for B, the theoretical enthalpy of lattice dissociation for silver chloride is plus 770 kilojoules per mole. Explain why this value is less than the value for silver fluoride. Well, if you think back to polarization, for something to be really, really good at polarizing, the ion needs to be quite small. And so fluorine and chlorine, they're both in group 7. However, fluorine is one above. So that means that the fluoride ion is much smaller than the chloride ion because it's got one less outer shell. And so that means that it's attracted to the silver plus ion more closely than the silver chloride ion. And so that's why the enthalpy of lattice dissociation is bigger because the ionic bonding is stronger. So the answer is that fluoride ions are smaller than chloride ions. And that means that we have stronger ionic bonding to that silver plus ion. And so the lattice enthalpy of dissociation for this silver fluoride is a lot bigger.